right, good morning. Okay, so once again, final exam reminder is Tuesday, December 13th, 1 p.m. in the Hall of Music, just like last time, the last two times. So make sure, as usual, find out where you need to go. Oh, by the way, we finalized the final exam. It'll have 20 questions. And so that means 10 points per question. Final exam's out of 200 points. So 10 points every question on the final exam. You should expect to see something in the neighborhood of 6 to 7 problems on the material since exam 2. So it's not going to be, especially weighted in any way. So around 6 or 7. Okay, let's continue our quest on finishing up this review set. Based on the survey, which I got quite a bit more response since Monday, so that's good. Based on the survey, we want to look at number 20 next. Number 20 says, find a vector that is normal to the graph of the equation 2 cosine pi xy is equal to 1 at 1 over 6, comma 2. Okay, so if you think about what's going on here, this graph here, this is a function of two variables here, implicitly defined. This is going to be a curve on the xy plane. Now what you want to do here is to think of this as the level curve of a function. So I'm just going to sketch that roughly. It's going to be something like that, right? Not exactly it, but you get the idea. I want to think of this function as the level curve of some function f of xy. Now the reason is because we know that the gradient vector is always perpendicular to a normal curve. Which is precisely what we want here. We want to find a vector that is normal to that curve. So if you think of it as a level curve, then you just have to find the gradient of that function at this point, and then you would have that normal vector. And there are many different ways to come up with this function. The easiest way here, I'm just going to define a new function f of xy to be 2 cosine of pi xy minus 1. So this curve is obtained when f of xy is always equal to 0, for example. So that's a level curve, right? Then the gradient of this is simply fx, fy, which is pretty easy to find. For this function here, we're going to get negative 2 pi y, sine of pi xy, and then partial derivative with respect to y will be minus 2 pi x sine of pi xy. Right? Then at this point, we're simply plugging x is equal to 1 over 6 and y is equal to 2. Very simple. And we get minus 2 pi y, so minus 4 minus 4 pi sine of pi over 3, radical 3 over 2, minus 2 pi x, that's negative pi over 3, sine of pi xy is sine of pi over 3, radical 3 over 2. So this is the same as negative 2 pi radical 3, negative, what is it? Radical 3 over 6 pi. Okay, then you look at the five answers here. None of these look quite like what we got. In fact, the clue here you need to be looking at is that all of these are integers. So we got a bunch of fractions floating around. Let's factor fractions out. And none of these answers contain a pi. So what's going on here is we found a vector, but we need to scale it so we can match one of the answers. We found a vector pointing in the right direction. We just don't know how long it is to match. So I'm going to factor a radical 3 pi over 6 out of this thing. If I take that out here, then this will become a 12. Okay, 12 times this gives me that. And this, of course, becomes minus 1. Rather, plus 1, sorry. Because I took out a negative here. So this is the vector that's on the answer sheet here. This is choice C. The answer. Okay, so again, the vector we found by doing the gradient is the right vector. It's just we don't know exactly how long it should be. And to match the answer, we just factor stuff out here and there until we see a part of that vector matches one of the answers on the answer sheet. Make sense? Questions? Okay, good. All right, we got 20. Let's see, what's the next one? According to my list here, number 32 is the next one. Find the area of the portion of the plane x plus 3y plus 2z is equal to 6 that lies in the first octant. Okay, so what we got here, remember how to sketch planes like these. If you just want to find out what's going on in the first octant, you just have to find the 3 intercepts. And to do that, you make 2 of these things zeros, 2 at a time. If you make y and z 0, then x is equal to 6. So that's the x-intercept. If you make x and z 0, then y is equal to 2, and that's the y-intercept. If you make x and y 0, then z is equal to 3, and that's the z-intercept. So that plane is going to slice through, and the portion in the first octant that we care about is that triangle. We want to find the surface area of that. Now this is in Cartesian already. So one thing you could do is to use the surface area formula. Who remembers the surface area formula? 1 plus, right, partial derivative of z with respect to x squared, and then partial derivative of z with respect to y squared, dA, right? And A is just the area living on the x and y plane. That's one way to do it. The second way is to parameterize this, like the way we've been doing, and then find the magnitude of RU cross RV, and then integrate over the region. It ends up doing the same thing, exactly the same thing. This is a result of the magnitude of RU cross RV business. But again, we have a Cartesian simple surface. This is probably the convenient way to do it. All right, let's figure out what solve for z first. And then so we can do these things. So z is going to be 3 minus 1 over 2x minus 3 over 2y. So partial derivative of z with respect to x is minus 1/2. Partial derivative of z with respect to y is negative 3 over 2. So this radical thing here is going to be just a constant. Very, very nice, just a constant. Now we've got to check out what the region on the x and y plane looks like, because that's what we integrate over. This thing will have a y-intercept of 2, x-intercept of 6. So this here is the region D that we'll be integrating over. We integrate this stuff over that. And once again, you have a choice of using a type 1 or type 2. It doesn't really matter. I'm going to go with a type 1. Let x be bounded by constants, and let y be bounded below by the x-axis. And above here, we need the equation of that. So that's going to have a y-intercept of 2 minus a slope of 2 over 6 times x. Okay, so then I can now find the surface area. I have to integrate x last. Integrate y first. And then radical of 1 plus 1 over 4 plus 9 over 4. dy 4 dy dx. Okay, the rest of this is very simple. This is just going to be radical 14 over 2 once you take it out, which we will. And then we're integrating y first time. There's no y in here, so we simply gain that. And now this is just trivial stuff. 2x minus x squared over 6, 0 to 6. And this will end up being 3 times radical 14. 12 minus 6, that's 6. 6 times that is another 3 times this stuff. So 3 radical 14. Okay? Questions? Good? Good. All right, moving on. Next one, according to my list, we should be looking at is number 12. This is a chain rule problem. We're given that W is U squared over V, and u is some function g1 of t, and v is some other function g2 of t. We don't know much about g1 and g2, except we know that g1 at 1 is 3, g2 at 1 is 2, g prime at 1 is 5, and g2 prime at 1 is equal to -4. And we're looking for the derivative of w with respect to t when t is equal to positive 1. So this one just testing if you know how to use chain rule to find derivative of w with respect to t. If it helps, draw the tree diagram here. W is at the top. It initially depends on u and v only. But we also know from the given information here that u and v also depend on t. So really, w ultimately depends on only one variable, which is t. That's why it's a regular derivative and not a partial with respect to t. And you remember how to climb down trees like that. You got to go 2 branches. Each time there's a split, you use the partial derivative. So following the left branch here, we need a partial of w with respect to u first, and then regular u with respect to t. The right branch is partial with respect to v, and then dv dt. Okay? The partial derivative of w with respect to u, that's very easy to find. 2u over v. du dt, u is g, so this is the same as g1 prime of t. Then the partial derivative of w with respect to v is -u squared v squared. And then dv dt, v is g2. So that's the same as g2 prime of t. Okay, this will work for any value of t that when these things are defined, we care about what happens at t is equal to 1. We need to know u and v at t equal to 1. U is the same as g1. So u at t is equal to 1 is the same as g1 at 1, which we know is 3. V is the same as g2 of t. At t is equal to 1, we're looking at g2 of 1, which is 2. And here we need g prime of 1, well, we know that, and g2 prime of 1, we know that too. So we toss all of that in. dw dt is going to be 2 times u at 1 is 3, over v at 1, 2, g prime of t, g prime at 1, g1 prime at 1 is 5. Here we have u at 1 is 3, so 9. We're squaring that over 4. g2 prime at 1 is -4. So we get, what do we get? We get 15 plus 9, which is 24. Okay, standard chain rule stuff. Questions? Good. So if a question like that show up, this is one of those questions that you should basically, count it as 10 points you have in your possession. So don't get stuff like that wrong. Just don't. Next one, according to what I have here, is number 9. Looks like we are mostly looking at older stuff. That's fine. That's fine. Level curves of, what is this? F of xy equal to 1 minus x squared minus 2y squared are what? That's what we're supposed to find. Okay, again, level curve, the definition of that is when the dependent variable is a constant. Some constant, we'll call that k. And therefore, we're trying to figure out exactly what shape we got when we're given this thing right here. K is equal to square root of 1 minus x squared minus 2y squared. And this shouldn't be difficult. This shouldn't be something that's going to be hard to do. If you square both sides, and then rearrange a little bit, put it into the standard, more standard note form that we're used to seeing, we get this stuff, right? Now we're going to assume that this k is such a way that this shape always makes sense. So, therefore, what shape are we looking at? Ellipse, right? X squared and y squared, positive sign in the middle. That's a circle if the coefficients are the same. If the coefficients are different, this is an ellipse. What if this is a negative? Hyperbola, right? Very good. Yep, so these are ellipses, depending on the value of k. And of course, there's certain values of k when this thing is not going to make sense, but as long as we stay with values of k such that 1 minus k squared is always greater than 0, then we're going to get a bunch of ellipses. Okay? Okay, next one. I think that's right. 54 appears to be the next one we'll be looking at. Jumping around back to the very end, the very last one. This one specifically tells you to use Stokes' theorem to evaluate a line integral f dot dr where f is equal to x squared zi plus xy squared j plus z squared k. And C is the curve of intersection of the plane x squared plus x plus y plus z is equal to 1, and x squared plus y squared is equal to 9, oriented counterclockwise. Counterclockwise viewed from above. Okay? Okay, so this is a very, very specific thing we're asked to do. So of course you gotta know what Stokes' theorem says. And what does it say? Well, how else can we write the line integral of f dot dr according to Stokes' theorem? Curl, right. And what? ds, dot ds, right? And by the way, remember that this dot ds is the same, it's a different way of writing dot normal vector ds with no arrow. Okay, so let's figure out what we're dealing with here. We need to know that normal vector. We have to know which way it's going to point. So first of all, we have let's start with a cylinder here. It's a cylinder of radius 3. And this thing goes up and down. Now it's going to go, we're looking at the intersection of that cylinder with a plane. This thing slices through the first octant with an intercept of 1 and 1 and 1. And what's the intersection of a cylinder and a plane? We've seen this before. Ellipse, right. We're going to have an ellipse that kind of inclines towards us, kind of like this. That's not so bad, right? You get the idea? It's an ellipse that cylinder goes up, and then we have a plane. We know what this looks like. It's got 1, 1, 1 as intercept, slices through like this. And the scales may not be right, but the idea is, hopefully should be clear. The curve, of course, is the intersection right here. This is our C. This guy right here. And we're told that if you were looking at this from above, you'll see this thing is oriented counterclockwise. So it should be going this way. And therefore, looking at that orientation, which way is the normal vector going to point? Up or down? And how do we know that? Right-hand rule, right? Exactly. So it's going to be pointing this way out. Okay? All right, so let's work a little bit with the curl.ds thing right here. Remember, we've seen this before. This ends up being the curl of f dotted with Ru cross Rv du dv. And of course, as usual, you got to make sure that's pointing the right direction. We have to make sure this happens. And the order may have to change, but we'll deal with that. Okay, so two things we have to do. First, we got to find the curl, and then we have to parameterize that surface. Let's do curl first. And the vector field we got is x squared z plus y squared plus z squared. Xy squared and z squared. Yep. And this shouldn't be hard to do, right? So let's see, the I component will be nothing. Is that right? Yep. 0I. The j component will be nothing minus x squared, and the negative of that, so plus x squared. And then the k component will be y squared minus nothing, y squared k. Zero x squared y squared. Okay, we'll come back to it. Now we're going to parameterize that ellipse. The ellipse, the intersection right here, okay, so the ellipse will have a projection onto the xy plane that looks like a circle of radius 3. And then the z will be slanted right here. And the z, as you can see, z is going to be dependent upon the plane because that ellipse is resting on the plane. X plus y plus z is equal to 1. So that means that z is equal to 1 minus x minus y. And you're going to put this together so you have a circle of radius 3. And then z is equal to that. Now, if you stay in the Cartesian, which is a good way to start, if you don't want to mess with the coordinate system, if we have to switch to cylindrical later, that's fine, but we can start in Cartesian. There's nothing wrong with that. Then the parameterization is very simple. If you let x be u, let v be y, then z will be 1 minus v, minus u minus v. So this will describe that ellipse. And we have to put the appropriate bounds on these things. So we can say that u is between minus 3 and positive 3, right? And v is between the lower half and the upper half of that circle. So we're probably going to be going to the cylindrical as we start the integration. Or another thing you could do right now is to change to cylindrical. Okay, let's try that because this looks like it's going to be kind of messy here. So this is a Cartesian. Okay, so x and y here are circles of radius 3. Right? And so, easy ways to do that for the x and y plane, u cosine v, u sine v, where u is going to go between 0 and 3. That's the radius of that circle, r. And then v is the theta, 0 to 2 pi. And then z is still the same thing, 1 minus x minus y, but we got to change x and y to the cylindrical equivalent. So that would be 1 minus u cosine v minus u sine v. Let me rewrite that. 1 minus cosine v, u cosine, rewrite that. 1 minus u cosine v minus u sine v. There we go. Good enough. Sorry about that. Okay, so I think we're going to go with the cylindrical here and just stick with it, finish the integration in that. Because if you had gone with Cartesian, looking at these bounds here, you don't want to integrate in those things. You would eventually go to cylindrical anyway. Might as well do that now. Okay. This is a long problem. But that's what it is. Okay, let's find the partial. Ru, looking at the bottom right here, cosine v, sine v, and minus cosine v minus sine v. And then Rv here, minus u sine v, positive u cosine v, and then u sine v minus u cosine v. Cosine. And then we have to cross this thing. It looks horrible right now. But remember, with trig things, often things look horrible to start. They often simplify quite nicely. So we're going to have to just kind of tough through the initial process here and find a way to simplify. Okay, cross them, u cross v. We'll worry about direction after we do the cross product as usual. First component will be u sine v squared minus u cosine v sine v, right? And then minus all of this stuff. So plus overall u cosine v squared plus u cosine v sine v. So it looks pretty bad initially, but look at this. These two guys go away, and what do these add up to be? Just u, right? In the end, this is just u. So not so bad. Let's go to the j component. Same story. U sine v cosine v minus u cosine v squared. And then minus all of this stuff. So negative u sine v cosine v minus minus, so another minus u sine sine square v. And by the way, because this is the j component, so all of these guys need to be flipped again. Right? And same thing happened here. U sine v cosine v minus u sine v cosine v. So these guys go away. And these together become negative u. And the minus here makes that overall just a positive u. Very nice. Lastly, the k component looks much easier now. U cosine v squared minus minus, so plus u sine square v. And that's the same thing we've been seeing in the other two components. So once again, it initially looks pretty awful, but due to the fact that we have so many trick things we can play around with, this turns out to be just fine. This turns out to be u, 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 right? Nice. Let's go back to our curl. We found out that the curl was in Cartesian 0 x squared y squared. Now we're going to go back to the surface that we parameterize here. In the k component, the negative x squared, we got to take the x component of the surface parameterization, u cosine, that's our x. So is it positive or negative? Positive, sorry. So the x component from the parameterization is u squared cosine squared, right? And then the y component from the parameterization is u sine square that, we get this stuff. Okay. Still remember what we're trying to do here? Yep. Oh, by the way, is this the right direction? Yeah. We wanted this to go upward, right? So this is the upward. So that's okay. Good. Okay, now we integrate. What are we doing here? We're doing integration of curl dotted RU cross RV du dv we dot these things now. We get u cubed cosine square v plus u cubed sine squared v, and u and v are both bounded by constants. We can go in any order. So I'm going to do v last and u first. Can you simplify this? That's just u cubed, right? We've been seeing that all over the place. So that's u cubed. So after all of this really horrendous looking thing, we end up integrating something that's really sillily simple. Right? This is all we're doing here. So this is 81 over 4 times 2 pi. So that's 81 pi over 2. All right, let's recap what we did here. Okay, so we're given a vector field. We want to integrate along some curve. That's the intersection of the cylinder and the a plane. And using Stokes' theorem, we know we have to do this instead of the line integral. Found out the direction of the normal vector. And then we did a curl, which turned out to be just fine. Then we parameterized the ellipse, and here's the little, the place where, that's not how you spell ellipse. There, ellipse. We parameterize that. I started with Cartesian, and then I look at this bounds here, and I look at these things. This is a pretty clear indication that Cartesian is probably not the coordinate system you want to stay in. So we try when to do cylindrical. And in cylindrical, we got a little bit of trig difficulties initially. But after a few uses of the nice identity, it turns out to be quite simple. Always check the direction of that normal vector, making sure it's the right one. If it's not right, you just put a minus sign in front of the whole thing. And then we used Stokes' theorem and then did a pretty simple integral in the end. Okay, questions about this? That's right, yeah. But the thing about parameterization is it removes all of that from things that you have to consider. Because this RU cross RV thing here, this will supply whatever you need in the right coordinate system. That's the whole point of doing parameterization. It removes this geometric thing that you have to worry about from the dA or dV. That's the whole, one of the major advantages of that. It takes the geometric thing out of the picture. You just so here's the thing, if you're parameterizing whatever coordinate system, it's always du dv. You never have to supply the extra stuff, like the extra r, the extra rho square sine phi, and all that. All of that will come out of ru cross rv. That's sort of magical, but it's taken care of by this piece of the puzzle. Other questions on this one? I think we have time for one more, so let me see. According to the list, which one is the next one? Number 5. Can we do number 5 pretty quickly? Number 5. Oh, we can do that. Yeah, we can do that just fine. Let's do number 5. Find the parametric equation of the line tangent to the curve. Oh, this, compared to what we just did, this seems really easy. But this happened so long ago, we probably forgot a lot of this stuff. And that's okay. Okay for now. Not okay next week. All right, so we're looking for the line tangent to this. So remember, for any line, we're going to need a point plus a parameter t and the direction v. More precisely, that's a vector from the origin to that point. And v is the direction. That's like the slope in your two-dimensional line. So if we want a line tangent to this curve right here, first we can find out the direction by taking the derivative. R prime of t, this is going to be 1, 2t, 3t squared. We're given a point, but we're not given t explicitly. But to find out the direction of this line that we want, we need to know t. So we have to look at this right here and figure out what t would give me this point. And that doesn't take a whole lot of time to find. T should be 2, right? 2, 2 squared, 2 cubed. Just simply by solving for t from these 3 equations. So the direction that we need is r prime of 2, which is 1, 4, 12. And this r0 is the vector from the origin to one point. And the point we got right here is 2, 4, 8. That's simple. So the line we want is going to be 2, 4, 8 plus parameter t times the direction 1, 4, 12. And we want the parametric, so that means we want to split up the x, y, z components. X is equal to 2 plus 1t, y is equal to 4 plus 4t, and z is equal to 8 plus 12t. Okay? All right, so we got one more day left. Make sure you look through the remaining questions, update the survey response if needed, and really make sure you tell me what you want me to work out on Friday. All right, that's it. See you Friday.